Now, in the last chapter, we looked at the conservation of energy, and we saw under what conditions energy is conserved, so energy could be used as a bookkeeping tool. So we're going to see that this concept of linear momentum can also be conserved in certain conditions, so it's going to be used for a bookkeeping tool. Okay, so I want to look at this concept of momentum that Newton had three and a half centuries ago. So Newton had this idea that this quantity momentum was a measure of a body's quantity of motion. Okay, so that sounds like a vague concept. How much motion does something have? So it's a composite idea between something's mass and its velocity. Okay, so again, everything in this class has mass. Okay, so next semester you'll be looking at light and things like that. But everything in this class has mass, and pretty much everything in this class is handheld or bigger. So if something's moving, then it has momentum. So here's an object moving to the right. Velocity points to the right. So the linear momentum is defined as its mass times velocity. And we use a little p for linear momentum. Now we use capital P for power, but we use little p for linear momentum. Okay? The linear part means it's moving along a line. Okay? In one of the later chapters, we'll do maybe a disc that rotates. We'll do a skater. Their arms are out like that. The skater rotates. We'll talk about their rotational momentum or their angular momentum. Okay. For now, we'll just look at linear momentum. And for now, we'll just call this thing momentum. We won't have to keep calling it linear momentum. All right. So, and the reason people think we use the letter little p is because Newton wrote about the impetus of the force. So the p comes from the word impetus, meaning there's something that gives this thing motion. All right. So something initially gave it motion. And so this is a vector equation. So if the velocity points to the right, then this arrow is also the direction of the linear momentum. Okay, so remember, that's a vector equation, so velocity points to the right, multiplying it by mass, that's a positive number, doesn't change the direction. All right, and the units are kind of strange. So it's just units of mass times velocity. So mass is kilograms, and velocity units are meters per second. So they're not grouped after someone and named after someone. Okay, so they're not grouped together and named after someone. All right, now, this concept of motion. So let's say I have a huge truck here that's moving. There's you in the truck. And here I have a little bug. That's a bug. Okay. So could the truck and the bug have the same momentum? Okay. Well, the mass of the truck is huge. So its speed would have to be small because the mass of the bug is small, so its speed would have to be huge. So there could be a case where the product of mass times velocity is the same for both. Okay, so that's the idea of linear momentum. It's a composite idea between mass and velocity. Okay, so now we have this new quantity, momentum. So we want to know, how is it related to the old stuff? All right. So in the old chapter, we had a mass. We said you applied a force, and the object accelerated. That was Newton's second law. Okay. So I'm going to write Newton's second law, but I'm going to write my acceleration as time rate of change of velocity. All right, and we're going to use, for this part of the chapter, we'll have an object of constant mass, okay, like your glider or something like that. So if the mass is constant, then I can move it inside the differential. So I'm taking the m and moving it inside. Okay, so the m is right there. And then this quantity, we'll see nature has decided that it has such significance that under some conditions it's conserved. So that's why now we call it something else. We call it the linear momentum. So if right here I have mv, that's what I'm calling the linear momentum. So now you can write Newton's second law, okay, not as F equals ma, but as time rate of change of the linear momentum. So back in the earlier chapter, we would say you apply a force, the object accelerates. Now, if there's a net force, the momentum can change. Okay, so I'm going to show you a video of something I have here. So I have two objects, okay. I have a spring attached, and I inserted a spring. I squish these things together by pushing my hand. So I compress the spring, okay. And to keep the objects from springing apart, I tied a rope. That's a rope. Okay. So these two things are held together by the rope. If the rope wasn't there, these things would spring apart to the left and the right. And here I have a little flame. That's a little candle. Okay, and when the candle burns the rope, these two things are going to break apart like the picture down here. Okay, so remember momentum is mv. So here I ask, what's the initial momentum of the system? Well, system's not moving, so initial momentum is 0. Okay, after the string breaks, okay, so candle burns the string, these things break apart. All right, I want to figure out, well, what happens to the system now? What happens to the momentum? Well, where these two things break apart, if this is my system, that force, this number, the spring pushes on number 1, spring here pushes on number 2. Those are internal forces to my system. Okay, so there's no external forces. There's no fingers that come by. So those forces are internal to my system, so there's no net external forces, so momentum's conserved. So initial momentum is 0, that means the final momentum has to be 0. Okay, so I wrote my final momentum as P1 final plus P2 final, okay, because there's two objects, so the final momentum 0. And so I brought this one over, and that says that that P1 final is equal to minus P2 final. So the final momentums are equal and opposite. So for example, if this momentum is 3, okay, if number 2 has a momentum of 3, and I'm making that positive because it points to the right, then momentum of number 1 would be minus 3, okay, with the correct unit. So they're equal and opposite. Okay. Here I put in P1 final is M1 V1 final, and P2 final is the vectors M2 V2 final. All right. So I wrote this over here. Okay. So I'm using the special case because in the video I'm going to show these two masses. These two objects have the same mass. So for M1 and M2, I just wrote it as M and M. Okay. So the masses drop out. Okay. So that says that they go away with equal and opposite velocities. So if number 2 goes off at 5 miles per hour, okay, then number 1, that says number 1, goes off at minus 5 miles per hour. They break apart with equal and opposite velocities. Okay. Now remember, speed is the magnitude of the velocity. Remember, speed is the magnitude of the velocity. Okay. So if I take the absolute value of both sides, that says they break apart with the same speed. Okay. So one way I can demonstrate that, okay, how do I know that they would break apart the same speed, is what I'll show is I'll put them in the middle of the track. Okay, so they start, let's say, the middle of the track. Okay, and then I press a button. So in the video I show each of the carts have little springs. I hit a button, spring breaks them apart. And if they're in the middle of the track, and if indeed that they break apart at the same speed, you're going to see in the video that they hit the end of the track at the same time. So that shows indeed that they do break apart with the same speed.